notation we are using here, and what is the kind of long range invariance used in this set of lectures. So just let me start with a vector in 3 dimensions. This is all you know, that a vector I can break in 3 components, x, y, and z. And sometimes these components are written like ax, ay, and az. Or you can write, if you like, ax as a1, ay as a2, and az as a3. So this a vector I can denote like a1, a2, a3. Similarly, the coordinate vector r I can write in terms of x1, x2, and x3. I can have another vector which is b, and its components are b1, b2, and b3. And I also know how to take the scalar product of vector a and b. That we all know that a vector a and b, the scalar product is a1, b1, a2, b2, a3, b3, and then I can write this in terms of sum over I, ai, bi. Sometimes this summation sign we avoid, and that is what is called Einstein convention, that if there is any repeated index, that is implied that there is a sum over that particular index. Now you all know that this scalar product or dot product of 2 vectors a dot b is invariant under rotation of the coordinate system, right? Because a dot b is like a dot a. If I take both the vector a, then a dot a square, that is the length of the vector, and length of the vector will be rotation. A dot b is the length dot unit a dot unit vector b, that is the length of vector a along the direction b. So that length under rotation will not change. So what I am telling here is that the scalar product of 2, 3 vectors are invariant under Lorentz under rotations. That is what we know for the ordinary vectors. Now let us just go to the Lorentz transformation. And in the Lorentz transformation, you know, this, suppose I have 2 frame S and S prime, and the frame S prime is moving with the velocity v along the x direction. Then the x prime and x are connected by these 2 transformations, and y prime and y and z coordinates, there will be no change there because the motion is along x direction. Now, you know, sometimes what people do is that they write this gamma factor, Lorentz factor gamma, as cos hyperbolic y. And if gamma is cos hyperbolic y, you can immediately use the relation cos hyperbolic square minus sin hyperbolic square is 1. And you can find out how the sine hyperbolic y, that will be gamma into v velocity. And then if you take the ratio of these 2, then you can get the tan hyperbolic y, what is just simply the velocity v. And now if I want to write down this, this Lorentz transformation in terms of this hyperbolic function, then x prime will look like this, and y time t prime will look like this. Cos hyperbolic y x minus sine hyperbolic y into t. T prime is cos hyperbolic y t and sine hyperbolic y x. Now compare this with 2-dimensional rotation, where you all know that x prime is x cos theta plus y sine theta, and y prime is minus x cos theta plus y sine theta. Now this 2-dimensional rotation in xy plane is very similar to this Lorentz transformation, but it is in x and t, but the rotation angle here is imaginary, because what is appearing here is cos hyperbolic functions. So like cos I theta is cos hyperbolic theta. So these are imaginary angles. So this Lorentz transformation or Lorentz boost I can think of as a rotation in xt plane, right, within some kind of imaginary angle, right? So that is something which people use it, and from here it is very easily you can see that t prime, anyway y and z are not changing. So from here you can easily check that, like here x square plus y, x prime square plus y prime square will be equal to x square plus y square. Here you can easily see that it is t prime square minus x t prime square minus x prime square will be t square minus x square. That is invariant. So please note here that in 3-dimensional vector, what is invariant is x square, ay square plus a square plus az square. But in Lorentz transformation, what is happening, it is t square minus x square is invariant. So there is a relative sign between the time and the temporal and the spatial coordinate. So we have to be careful in define the vectors, right? So you know, this Lorentz transformation is similar to the, as I mentioned already, it's like a rotation in two-dimensional plane with imaginary angle. Now in Lorentz transformation, the time t and the spatial coordinate x, y, z, because of that invariant, it is coming into the with different sign, like d square minus x square. But here in our three-dimensional ordinary spatial coordinates, all the signs are same. So this negative sign is coming, relative negative sign is coming into the picture. Now in Lorentz transformation, it's not only the spatial coordinate, this time is intimately connected with the spatial coordinate, because in special theory of relativity, the time and spatial coordinates has to be put in the same footing, right? And then if we want to make any transformation, or any if I want to define any vector, like when I define the three-dimensional vector with three x, y, z component, if I want to define a vector corresponding to the Lorentz transformation, I have to take time into account. And then I have to also remember that when I evaluate the invariance, the time and the spatial coordinates, there is a negative sign. So this x mu, like I have written there, the a vector as a1 component a1, a2, a3, I can, or ax, ay, az, I can write a vector x mu in four-dimensional plane t x, y, z, because it should be actually ct, but we are working with a unit where c is 1. So x mu is equal to t x, y, z. Now the dot product of two vectors remains invariant under rotation. Similarly, I need to construct a vector of this x mu vector, length of this x mu vector, which should be invariant under the Lorentz transformation. And I know that the Lorentz transformation invariance is t square minus x square minus y square minus z square. So I should define a vector, another vector, right, where there will be this relative sign between t and this x, y, z, and that vector is defined as, that vector is defined as x mu, right? X subscript mu. So this is x mu t x, y, z, and this is x t minus x minus y minus z. Now if I take the scalar product of these two vectors, then x mu will be t square minus x square minus y square minus z square. So that will remain invariant under the Lorentz transformation, right? So that is the reason I have to define this contravariant. This is called contravariant vector, and this is called the covariant vector. And the length of that vector, is invariant under the Lorentz transformation. Sometimes I should write x mu, sometimes I'll just write x square simply. So this remains invariant, and this relative sign, is coming once I have a contravariant vector in this fashion and covariant vector in this fashion. Now the vector x mu, this covariant vector x mu, I can get from this contravariant vector x mu by multiplying this by a tensor j mu nu, which is called Minkowski tensor or metric tensor, with g mu nu equal to 1. This is actually a matrix, 4 by 4 matrix with all the diagonal components non-zero. This the time component is 1 and all the special component is -1. So that when I multiply this x nu, the contravariant vector, which has all the component positive sign, when I multiply by this, except for the temporal component, all other components will get a negative sign. So x mu will be just simply the x mu magnitude will remain same, but only the special component will appear with a negative sign, and that will remain invariant as that is the case for the Lorentz transformation. Now we can also construct the Lorentz vector, 4 vector, not for the special space-time coordinate x mu. I can also construct the Lorentz 4 vector for the 4 momentum, where p0 will be is this temporal component of this 4 vector, and pox, pi, pz are the 3 special components. And then its covariant component will be again g mu nu times this p nu, where this will be p0 and then minus px minus py minus pz. Okay, and then if I take the product of these two, p mu and p mu, I'll get p0 square minus px square minus py square minus pz square, which will be equal to p0 square minus p square. Now this p0 is the temporal component of the momentum 4 vector for a on-shell particle or real particle which obeys the Einstein relation. This P0 could be the energy of the particle. Now, if you put here energy, then it is E square minus 3 momentum square, and that E square minus 3 momentum square is the mass square, which is again an invariant quantity, right? And this is true only for the on-shell particle. So P mu, this is also a invariant quantity under Lorentz transformation. Now I can have scalar product or dot product of P and X. So P dot X is P mu X mu. So this P is contravariant P mu up there, right? So that is P, all the components will be positive, but when I am putting the index below, then except the temporal component, other will be negative. So if I take again the product, it will be P0x0 minus PXX minus PYY minus PZZ, which I can write as P0x0, and this is minus P3 vector dot X3 vector. And for on-shell particle again, this P0 I will be able to put E. So then again P dot X, this 4 vector product, I will be able to write as energy time minus P3 vector dot X3 vector. Now this is what I have said just about the notations and all which I are using. Now here I have discussed something more mathematical about the contravariant and covariant vectors, right? This I will come back later after my lecture. Here it is given in very detail why a vector is called contravariant, why it is called covariant, what is the exact mathematical transformation. It is there, but this mathematics I'll discuss a little later. Let me go back to the main topic today, and this is very interesting. But I'll tell you why the name even came covariant, contravariant, all that. But let me go back to the with this I can go back to the our main topic, and then I'll come back here. Okay. So what I have done yesterday is that we have written down the Lagrangian for the scalar field, and that Lagrangian for the scalar field. Just let me go through this. I'm getting back to the lecture today, so with that notation, I think I should be able to do it. Yeah. Okay. So what we have done yesterday, other day, is that we had this Lagrangian L for the scalar field, which I had constructed for the scalar field phi by demanding that this kind of combination will be Lorentz invariant. And I had written down the action for this Lagrangian, and from that action I had got this equation, which is Klein-Gordon equation for the scalar field phi. Now the scalar field phi, I have shown that this equation, if I take a Fourier transform of this equation with respect to spatial coordinate x, then this becomes a oscillator for the harmonic oscillators. But I have shown that the frequency of the harmonic oscillator omega was, yesterday you have seen that it goes from omega is equal to p square plus m square, and since p can take infinite number of values, so I have a collection. This represents that Fourier transform equation represents an infinite number of harmonic oscillators. So infinite number of degrees of freedom has come to our theory already. And then with the analogy with the harmonic oscillator, right there, the dynamical variable was x, and the dynamical variable I was able to write in terms of 1/2 root omega a plus a dagger. Right now, here my dynamical variable is phi, so it is also written as 1/√2 p omega a plus a dagger. But then I have infinite number of oscillator. So because of this infinite number of oscillator, for p equal to 0 to infinity, it can vary. So I had the integration over this p. So this was the expansion of this field phi, this field operator phi, in terms of the annihilation and creation operator, right? So that is what we have seen yesterday. And then if phi have this kind of expansion, then I have the pi, what was correspond to the dynamical variable p in classical mechanics. And then when we went to the quantum mechanics, we had promoted the dynamical variable p to operator p, and that operator p again we have written down, if you remember correctly, it was minus I times omega by 2 a minus a dagger. So then what I did, I used the similar argument then because I have infinite number of oscillators, I wrote pi x as a integrations over this, right? Now please remember that yesterday what I have done, I have shown you, I have mentioned there, even in the note which I had sent today, that I had put the time t equal to 0 there, because you see in this side, right hand side of phi x and pi x, there was no time. This is p vector x, p vector x. So today I want to introduce the time variable, because after all, when I will be going to do the quantizations, then space and time has to be put in the same footing. The time dependence of an operator, you all know, if phi is the operator, right, at time t equal to 0, then at any time t, I can calculate the operator by using the Heisenberg picture, by operating, you know, e to the I h t, where h is the Hamiltonian of the system, and here e to the minus I h t. So this, if I know the phi at any particular time, I can calculate the phi at any later time by you know, operating or by doing this exercise, right? You also know that this in harmonic oscillator, in analogy with harmonic oscillator, you have seen that this h, the Hamiltonian of the harmonic oscillator, which will ultimately come as you know, a dagger a into h bar omega plus the 0 point energy, of course, but that 0 point energy does not contain any operators. So the h and a, this commutator you can easily calculate, and you can show that is frequency times minus frequency times the annihilation operator. And similarly, the Hamiltonian the commutator of the Hamiltonian with the creation operator is omega times the creation operator. This you know, right? Now you also know the Heisenberg equation of motion for the operator O is I d O dt. The O is the operator and commutator OH. Now this, if I take put A here in the Heisenberg equation, then my equation becomes I dAp dt equal to the commutator AP with H. Now I know that the commutator H AP is equal to minus omega P AP. So I have a equation now, I dAp dt is equal to omega into AP. And this equation has a solution that AP at time t will be equal to AP at time t equal to 0 multiplied by e to the minus I omega t. Right? So this is how the time of the operator A, relation of A is coming into the picture. Now in a similar fashion, which you can do in place of O, I can place AP dagger, the creation operator, and again I solve the equation, and I can show this AP dagger will be e to the I omega pt into AP dagger, which is missing here. Or if you want to do it in this way, if you want to see what is my A operator here, e to the IHT, A operator at time t equal to 0, let us say, e to the minus IHT. So that also you can do. What you can do here, APT as is to the IHT, AP e to the minus IHT. Now you expand this for small, you know, value of HT. So keep the first term 1 plus IHT, AP 1 minus IHT. Then you can write this is equal to AP, and then you see you'll have multiplication like HAP and then APH. So you will get a commutator HAP into T. Now HAP commutator, you know, again it will come in terms of the, it is minus omega p into AP. So your APT will be AP into 1 minus I omega p into T, which if this is for the small, you know, infinitely small transformation, for finite transformation, it will come as an exponential, and APT will appear as e to the minus I omega pt into AP. So this is how the creation operator, annihilation operator, time dependence comes into the picture. Similarly, you can do for the creation operator. Now, therefore, this phi tx was my d cube p by 2 pi cube 1 by 2 omega p, and I had AP e to the minus ip dot x. Now, because of this time dependence, I have e to the minus I omega p t. So now I have full time dependence of the operator, field operator phi, and AP dagger was e to the I omega p t. Now I can combine this. You see, as equal to e to the minus I omega p t minus p dot x. Couple of minutes ago, I have discussed that e to the I p dot x is equal to p0 x0 equal to p0 x0 minus p dot x. So this is this omega p is like p0, x0 is like t, right? And for the AP dagger, it was omega p, which is p0, and this is x0 minus p dot x. Just I have combined these two exponential. And this omega pt is a p dot x, and this omega p, I have yesterday shown you, this is nothing but the energy of the particle. Because after quantizing, we have seen that the Hamiltonian comes as of the oscillator system comes as the number operator a dagger a, right? Number operators a dagger a into omega. So into omega p, and then that omega p, then I have again calculated the momentum of the system, and we have seen that the p which appears in the omega, that is really the free momentum of the oscillator. So then we have identified that omega as the energy of the particle, p is the momentum. That's how we got the concept of the particle as the excitations of the fields or quanta of the scalar fields. And then EPT, again I can write P0 x0 minus P dot x, which is simply sometimes written as P dot x. So this whole exponential I can write phi tx as this integral time e to the minus px plus AP dagger e to the I P dot x. Now, so please, it is easier to remember that the annihilation operator comes with a negative sign. Annihilation, which reduce particles from the system, it comes with a negative sign, and the creation operator comes with the positive sign. But this P dot x, please remember, it is not a 3-vector product, it is a 4-vector product. P0 x0 minus P vector dot x, right? So when you put the time dependence, what appears is that this remains same, and AP e to the minus I P dot x plus AP dagger e to the plus I P dot x, where this P and x are the 4-vector. Okay. Now, we know that we know the Lagrangian of the system, so I can take the derivative of this Lagrangian. Oh, this should be L. Lagrangian or the derivative of Lagrangian with respect to this thing. No, this is fine. This is fine. So this pi comes as d phi dt. That we have seen that if I take the derivative of the Lagrangian density with respect to phi dot, then what we got a phi dot is d phi dt. So this is okay. This is equal to phi dot. So if I know the expansion for phi, I can easily take the time derivative of that and get the expansion in terms of for the conjugate momentum p pi. So then the pi, the conjugate momentum operator, is given by this particular expression, right? And here I have just written a few things which is not so important here, but I will come back to this. Now, to understand the now I understand we want to understand the whether as in the very first lecture I mentioned that if you calculate the probability amplitude of a particle propagating from a point x0 to x, we have seen that amplitude is non-zero for any arbitrary value of x and t. So that was not acceptable. That violates the special theory of relativity in letter and spirit. So we had to that was the inconsistency of the between the non-relativistic quantum mechanics and the special theory of relativity. Now we need to understand whether by doing this exercise which we have done already, whether the causality of the system is restored or not. So to understand the causality of the causality in question, what we can do, we can ask the following question: that suppose I have 2 points separated by space-like vectors, space-like separations. What is space-like separation? That is what is discussed here. Suppose you have a 4-vector A mu, which it will have a component A0 and AX, AY, AZ, let us say, and then this is a covariant vector. It will have a component A0 minus AX minus AY minus AZ. So if I take a product, it will be A0 square minus A3 vector square. And if this A0 square minus A square, this vector, this magnitude is less than 0, then we will call it a space-like vector, space-like separation. So if A0 square is less than a vector square, then that is a space-like separation. And a separation will be called time-like if A0 square is greater than A square, right? and it will be also called right like if a0 square is equal to a square. You can understand this from the, if you write down the 4-vector operator of x mu and x mu, which we know that it is x0 square minus x square, but x0 is time, right? So x square minus, so t square minus x square. Now dimensionally, what happens is it is not actually t because of the unit it is coming as t, but it should be ct. So ct square minus x square less than 0. That means ct less than x, that is the space-like domain, right? So that is the space-like domain. And in the if you have a space-like, and if ct is greater than x, ct square c square t square is greater than x square, then that is a time-like domain. Okay, in the space, so space-like domain will indicate that is the domain where we want to see whether the particle can propagate there at all or not, because that there you are, if you write here ct is equal to ct less than x, that means the c becomes less than x by t. That's not allowed for a relativistic particle in classical mechanics. So to understand this causality, what we are going to do here is that we will be asking the following question. Suppose I make a measurement at 2 points, and those 2 points are separated by space-like separation, right? So I want whether the measurement of 1 point will affect another point where those 2 points are separated by space-like separations. Okay. Now to understand that, we can calculate the phi x, this commutator phi x and phi y, right? And where x and y are 2 points which are separated by space-like domain. Okay, space-like separation between x and y. So that is what we want to calculate. You remember that the famous the commutation relations between x and px. X and px commutation is non-zero. That means that the measurement of x and px you cannot do independently. They have to obey the uncertainty principle. But x and py, right? X and pz, those commutators are zero. So we want to see that whether this commutator phi x phi y, where x and y are space-like separation, separated by space-like domain length, then phi x and phi y, whether this commutator is zero or non-zero at the space-like domain. So all space-like separated operators will satisfy the commutation relations phi x phi y equal to 0. That means this x minus y is, where I am saying that it is space-like, then x minus y whole square, which is actually 4-vector square, is less than 0. Because when the 4-vector square is less than 0, 4-vector square is a0 square minus a square. When that is less than 0, that is the space-like domain. So we want to see whether this phi x phi y, which we have already written in terms of the annihilation and creation operator, that commutator is 0 or not. And let us do that calculation. Okay. So if that commutator is 0, that will imply that the measurement at x not affect the measurement at y, if x and y are not causally connected. When in the space-like, when the 2 points are space-like separated, then they are not causally connected, because as I said here, because there you get the c value which will be less than x by t. X by t, if you call it velocity, then that is that c is becoming less than x by t. So that space-like domain is not causally connected. So what I want to do then, this we want to calculate this phi x phi y, this commutator, and see whether in the space-like domain it is vanishing or not. Okay, so this commutator is phi x phi y, which I am denoting by delta x minus y. Okay, so now delta x minus y is phi x. I will write phi x phi y minus phi y phi x, and I know what is phi x. Phi x I know in terms of this annihilation and creation operator. Phi y is annihilation and creation operator. Here again, this should be phi y, and then again phi x. So just what I do the simple multiplications, And by this time I know, yesterday I have shown you that the commutation relation between A dagger is 0, A dagger is 0, right? Those commutators are 0. So if you take the product, if you easily see that only non-zero product will be, commutator will be AP dagger prime and AP dagger AP prime. These two will survive. Now, you know, yesterday we have derived these commutation relations. If I put these commutation relations here in terms of the Dirac delta function, then I can use the Dirac delta function, this 3 Dirac delta function, to do the d cube p prime integration, right? If I do the d prime p integration, then what I get, that delta x minus y, the commutator phi x phi y, is this particular quantity, d cube p by 2 pi cube 1 by ep e to the base. Now, few observation I would like to make here. This delta x minus y is Lorentz invariant, because you can check that d cube p by e is always a Lorentz invariant quantity, because if you write down the d cube p as dpx, dpy, dpz by divided by energy, you know, out of those, since I am considering the motion along the x direction, then dpy, dpz will remain unchanged, but dpx by e will become, right, dpx prime by e prime, and you can easily check that dpx prime by e prime will remain invariant. So this quantity is Lorentz invariant. And anyway, this p dot x minus y, this is a Lorentz scalar, because the 4 vector product of p vector, p4 vector, and the space and the x minus y, this space 4 vector. So this is a Lorentz invariant quantity. Okay. Now let us first see whether delta x minus y vanished in the temp, for this time-lax domain. So x minus y, this is the special separation. I can take this as t and all the special component at 0, and this will represent a time-like vector, because t square minus 0. What was the time-like vector? Time-like vector was, let me go there. Time-like vector was temporal component square minus special component square. That was the temporal square minus the special component square. If that is less than 0, then it is space-like, and if it is greater than 0, then it is time-like. So if I take my x minus y as t00, then my temporal square of the temporal component, anyway this special component is 0, so this square of the temporal component is greater than 0, so this is a time-like domain. So if I take x minus y is equal to t000, then I am in the time-like separation. Okay, so then what you can do, you can put here the p dot x minus y, only p0 times x minus y is t will be there, and p vector minus dot x vector minus y vector, that will be 0, because all the component of x minus y vector is 0. So this delta x minus y will be this quantity times e to the minus p0t into the I p0t, and you can see that this will be never be 0. So the commutator, this will never be 0. This will be always non-zero. So in the time-like domain, this is non-zero. But let us see what is happening in the space-like domain. So in the space-like domain, what is happening? Delta x minus y is non-zero. Now space separation at the 4 vector square will be negative. In the 4 vector square, if I take temporal component is 0, then I have only the special components which comes with a negative sign. So this will be always less than 0. So if I take the x minus y vector, x minus y 4 vector as 0 as a temporal component, and x 3 vector minus y 3 vector as the special component, then my delta x minus y will be this, right? Now delta x minus y for special separation will be like this. Now I have two integration, d cube p 2 pi cube e to the I p dot p here is a 3 vector, because the temporal component I have taken as 0, p vector dot x minus y vector minus e to the minus p x minus y vector. So I have two terms here. What I do, first term I keep as it is, and second term I change the variable p to minus p. When I am saying I am changing the vector p to minus p, I am setting px equal to minus px, py equal to minus py, and pz equal to minus pz. So this vector, let me just explicitly do it here because there was some confusion yesterday. So this dqp is dpx minus infinity to plus infinity, dpy minus infinity to plus infinity, dpz minus infinity to plus infinity, and then this ep is root over p square plus m square e to the minus I p dot x minus y, right? Now I have to change the sign. So dpx had a negative sign, a negative sign, and negative sign. And then I should also invert the integration limit, right? Infinity to minus infinity. So, right, that is what I have to do. And then this will not change sign because it is a function of p square. And this has become just plus, right? This has just become a plus sign, right? Now, there will be negative sign, one negative sign coming from here when I will invert the integration from minus infinity to plus infinity. So there will be 3 negative sign. Already I have 3 negative sign. So 6 negative sign will give me nothing. So this will not change at all. Only what will change, this exponential will change the sign, and exponential will change the sign. So if the exponential change the sign, then the second term and first term becomes the same. So it is becoming 0. So the commutator for this space-like domain is becoming 0. That means that the measurement of phi x and phi y, the measurement of phi x and phi y at the point x and y, where x and y are separated space-like, then there will be the measurement will at point x will not be affected by the measurement of y if x and y are separated by space-like. Right now, you know, this delta x minus y, I said that this is a Lorentz invariant quantity. So if it is Lorentz invariant quantity, then this phi x phi y will remain, will vanish because this is Lorentz invariance. It will remain, it will be vanished for all other cases. Where I have taken this particular example, but it will be vanishing for all other cases. So that is what. So that means that, you know, they somehow for this commutator the quantization conditions has you know, the causality is restored. I'll come back to that more detail when I'll quantize this complex scalar field. Now, you know, we have also discussed about the complex scalar field, which is L del mu phi star minus m square phi star phi, right? This is the Lagrangian for this complex scalar field. Yesterday I have introduced 2 real field phi 1 and phi 2 and shown you how I can combine them to write a Lagrangian for the complex field phi and phi star. And you know, I want to derive the Euler-Lagrange equation. If I take the derivative of this with respect to phi, then I get the Klein-Gordon equation for phi star. Now, if I take the derivative of this L, functional derivative of this L with respect to phi star, then I get the Klein-Gordon equation for the variable for the field phi. So this is for phi star and phi. Remember, when I am getting the equation for phi star, I am taking the derivative with respect to phi. And when I am taking the getting the equation phi, when I am taking the derivative with respect to phi star. So these are the 2 equations. Now, you know, now corresponding to that phi and phi star, I should have 2 variables. One is pi del L del phi dot. Remember again that classical mechanics del L del q dot, right? So q was the dynamical variable there, phi is the dynamical variable here. So there the momentum was p, here the momentum is pi. So del L del phi dot, which if you take the derivative of that L, you will get it is phi dot star. Similarly, I can take the, you know, for the complex part, pi star will be del L del phi dot star, which will be just simply the phi dot. So I know the 4 variables now: phi, pi, and phi star, pi star. So these are the 4 variables which I have instead of 2 phi and pi for the real field, because the degrees of freedom is just doubled here. Okay. Yesterday there was a question that why I am not taking a derivative with respect to, why I am taking derivative with respect to phi dot is time derivative, why I am ignoring the space derivative. So somebody was asking, if I take a derivative with respect to del mu phi, You see, if you introduce a mu, del mu, then that will not remain a scalar. This pi will not remain a scalar. But we are discussing scalar field, so phi and pi both has to be scalar. Okay. Now the quantization condition, again I put as pi is I, Dirac delta function. Again remember, xp was I, h bar is 1. So or xi pj equal to I delta ij, Kronecker delta. Here I have written pi x equal to I and this Dirac delta function. So here remember one thing, I have taken the equal time, that the time for the variable phi and the variable x is same. Now these other commutators are also, all these commutators are 0. Now the phi field I can expand in terms of again annihilation and creation operator, but I should be careful because phi is not real. Phi is not real, it is a complex field. So I have introduced a field here AP, right, e to the minus ip dot x, and here another creation operator BP dagger e to the minus ip dot x. If I take AP dagger here, then phi star will be phi, that will indicate that my field is scalar field, a real field. Similarly, phi star will be just the complex conjugate of that, AP dagger e to the ip dot x, BP e to the minus ip dot x. Now suppose you have a, so what they will do this, suppose you have a AP, and that AP will annihilate a particle, and BP dagger will create an antiparticle. Phi star AP dagger will create a particle and BP will annihilate an antiparticle. So 4 operators. Now for the real particle we need one operator to create, other to annihilate. But here I have phi and phi star. So I have we'll see that there are particles and antiparticles. So to create particle we need AP dagger. To annihilate particle I need AP. To create antiparticle I need BP dagger, and to annihilate antiparticle I need BP. Right? I'll show you how why I'm talking them, telling them particles and antiparticles. Okay. So since I know the commutation relations for phi and pi, I can put this expression, of phi and pi. I can put these expressions in the commutation relations, and then I will get the commutation relations for A and A dagger, B and B dagger. This exercise we have done in detail yesterday. This is just the extension of that. So don't have to worry. You just go to the next other day calculation. You will get everything. Okay. And now, so this is for A dagger. This is the commutation relations, and B dagger, this is the commutation relations. All other commutations will be 0. Now I define a number operator NA, which is for the A kind of particle AP dagger AP, and for the B kind of particle NB another number operators for BP dagger BP. And when the AP operates on vacuum, gives me 0, because in the vacuum I am assuming there is nothing, so there is nothing to kill. So when annihilation operator operates on the vacuum, it becomes 0, and BP when it operates on 0, it gives me 0, right? Now from there, again for this complex system, I can calculate the Hamiltonian, which is the minus L, right, plus pi dot, right? This is for the real field, and then plus pi, for the field phi, and then plus pi star phi dot star for the, this is for the complex field, right? So like if you have in the classical mechanics, H equal to minus L plus P1 Q1 dot plus P2 Q2 dot. Similar here. If you have more degrees of freedom, then the Hamiltonian will take this form. Now I know the Hamiltonian density. I can integrate over d cube x, so that I will get the total energy of the system. And I know pi in terms of annihilation and creation operator. I know phi dot, I know pi star, I know phi dot star. All these quantities I know in terms of the annihilation and creation operators. So I just put that in the expression for H. You will get the Hamiltonian as d cube p by 2 pi cube EP, AP dagger AP. This is the number operator for the A A kind of particle, and BP dagger BP for the number operator for the B. And there are two commutators like AP dagger and BP dagger. Again, please note that these commutators will give rise to Dirac delta function with zero argument, because if P and both becomes, if P becomes equal to P prime, then it is Dirac delta 0, which will diverge. So there are two divergence quantity, and that is not surprising, though it is disturbing. It is not surprising in the sense that you have infinite number of oscillators, and each oscillator has an energy in h bar omega by 2. So if you add up the infinite number of them, then you will get infinity. We'll see how to get rid of this. So this is correct. Like you have two sets of harmonic oscillator. One corresponds to this number of A kind of oscillators and B kind of oscillators, and there are infinite number of them. So there are two other infinities. Now again, please recall that we have calculated yesterday the momentum Pi, which is given by pi, the conjugate momentum, times delta I phi into d cube x, right? Now this again, momentum I can calculate. I can write down the pi in terms of annihilation creation operator, and phi I know I can take the special derivative. And then momentum, if you calculate, you will get d cube P by 2 pi cube, 3 momentum P, AP dagger AP plus BP dagger BP. So this is P times number operator for the A particles and number operator for the B kind of particles, right? This is all fine. Now we have earlier also shown that the conserved current for the scalar field is J mu is equal to I into phi star del mu phi minus phi del mu phi star. This is the Noether currents, and yesterday or maybe day before I have derived this expression. Now you all know that this J mu is a 4 vector, right? Its temporal component is the density, and the spatial component is the current density J. So J mu is also a 4 vector, Lorentz 4 vector. This is rho and this is J, right? Temporal component and the spatial component. Now this temporal component of this I will get if I take mu equal to 0. Mu equal to 0 means time derivative. So this rho will be I phi star del phi del t minus phi del phi star del t, right? So then my rho is this. What I can do, this phi star and del phi del t, you know, is nothing but pi star, and phi del phi star del t, you can check the Lagrangian, it will come as pi. So this we have done already. So suppose this is the probability density or density of the system. Then if I multiply that by the electric charge, say the particle phi and phi star, they have some electric charge. So if I multiply that by electric charge, then this becomes the charge density. So please note, then rho, you multiply which I got from the Noether currents, and then multiplied by E, then this is the charge density. So this is my charge density. If I and you remember, if I integrate over this charge density, I will get the total charge, and I have shown you that the time derivative of the total charge is equal to 0. That was actually the Noether's theorem. It says that if if you give a global gauge transformation, and under that global gauge transformation, if the action remains unchanged, the total charge will be conserved. So that is what we have seen other day. So rho is the charge density. So if rho is the charge density, it is coming as a in terms of the pi star and pi and pi star, pi and pi star. I know the expression again in terms of annihilation operator and creation operator. I know pi, I know pi, I know pi star, I know pi star. I will put everything, all the expressions, and then I will do little algebra. And this algebra, if you do the detailed algebra which I did yesterday, it is same technique. So that is why I am not repeating. It is exactly the same technique. You will take the total charge of the particle will be E d cube B by 2 pi cube 1 by EP minus A dagger A minus B dagger B. A dagger A is the number operator for A kind of particle, and this is for B kind of particle. See, this is a very interesting result in the sense, you see the number for the Hamiltonian, go back here, it's very interesting that in the Hamiltonian, the A and B kind of particles are just adding up. Number operators are N plus B. For the momentum also, the operator adding up. Number, or if you want to call it number, let's say number adds up. Because in energy and momentum, suppose you have a system of particle and you have different kind of charge particles. When you calculate the energy, you just add up the total energy, right? Total kinetic energy of those particles. And for the momentum too, you just add up their momentum, right? But please note that in the charge, total charge, they are coming with the opposite sign, right? So that indicates that there is a relative change in sign between the particle A and B, right? That means if particle A has a positive charge, then particle B will have a negative charge. So then that indicates that if A kind of particle you call them particle, then B kind of particles are antiparticle. So automatically the antiparticle has appeared in your theory. You see, this is very interesting. But please note that the Hamiltonian, they are just added up. But in the total charge, they are coming. We have not done anything. We have not introduced this minus sign by hand. What we have done here in the Neudard's probability current, I have just put them in terms of the annihilation and creation operators. And in the Hamiltonian, I get they adds up, momentum they adds up, but in the total charge, they are coming with a relative negative sign. So if A is a particle, then B must be its antiparticle. Why I am calling this? Because their mass is same, right? Because they are adds up with the energy E, which is P square plus M square. So their mass is same, right? They are, as I said yesterday, that kinetic quantum theory describes this spin zero particle, and I have shown you that commutation relation indicates that they are bosons. So all the other properties of particle A and B are same except the electric charge. And then A, so then if I call A as a particle, then B must be its antiparticle. So that's how the antiparticle comes into the picture. Right? This is what in detail written here. Now, one more. Let us see. We'll see that calculate the propagator, and then we'll get back to the question of causality again. And this will be more clearly shown here. How the causality is restored by the quantizations of this of the field. Okay. So for that, let us calculate something which is called propagator. And this propagator is an extremely important quantity. We should remember, because ultimately after two or maybe after 2 classes, when I will introduce the Feynman diagrams, this propagator will come as a internal line. So let us understand that what is propagator. So suppose we have a particle at some space-time point, right? What is the probability that it has propagated to another point x, right? How can you do that? See, this phi y, suppose you have a particle at y, so you have to create a particle at y, and this phi y field is d cube p by 2 pi cube by 1 by 2 ep, ap e to the minus ip dot y plus ap dagger e to the ip dot y. So this is phi y, right? And if I operate this on vacuum, you see this ap will operate on vacuum and give me 0, but ap dagger will operate on this vacuum and create a particle at the point y, right? Similarly, so phi y on vacuum will create a particle y, and then 0, this is the Kent vector and this is the Bragg vector. If phi x on this will annihilate a particle at x. So if I take the scalar product of these two, what that will indicate? That will indicate that I have created a particle at y, and then it has propagated up to x. So what is the probability that the particle goes from y to x is given by the expectation value of field phi x and phi y within expectation value in this vacuum 0. Okay. So again, the technique is very extremely is same. So now again, I want to calculate the expectation value of this. What I do, I will put phi x and phi y in terms of the again annihilation and the creation operators. Now I don't have to do the full calculation, because if I have phi x and phi y, then phi x involves a annihilation operator and a creation operator. Phi y will also have a annihilation and creation operator. So when I'll multiply them, I'll have two annihilation operators. When I'll have two annihilation operators, then expectation value of two annihilation operators, that will give me 0. Because annihilation operator operating on vacuum will give me 0. That is the definition of vacuum. When I will have two creation operators, that will also give me 0, because I will be creating two particles, right? So you have a state with two particles and you have a vacuum, and they are orthogonal. The orthogonality will give you 0. So only term, if I take the product of phi x and phi y, only term which will survive, that will be AP, and when the AP dagger, right? This will give me the only non-zero term, because this is the term which will give me non-zero. Okay. Now, we know that from vacuum we can create particle AP dagger. This is the creation operator, operate on 0, and give me a particle with momentum p. And just I have put here a 1/2 EP root. This is a simply the normalizations for the there is a reason to put that. So that will mean that p vector is √2 EP AP dagger 0. Okay. Now then this AP prime dagger 0 will be simply, if you put this relation, you will get 2 EP, right? 2 pi cube Dirac delta function, and this 2 EP prime will come from this will come EP 2 EP, from this it will come 2 EP prime. So this is what will come, and you can see that it will get because of the Dirac delta function, you can use the trick that p should be equal to p prime. So this √2 EP into √2 EP will give me 2 EP, and 2 EP will get cancelled, we'll get this. Okay. Now here I have given a reason why I am saying that p, a particle with momentum p, is just, if I operate a creation operator on vacuum, it gives me p. I'm not saying that I am putting a 2√2 EP factor here. Why? I have explained that in this particular note in detail, that why that 2 EP factor will come. 2 EP factor will come because Dirac delta function d cube p, this Dirac delta function you can write as a product of 3 delta function dpx, dpy, dpz, and then if you take the Lorentz transformation along x direction, dpy, dpz will not change, only this px will change. If you change this px prime, px to px prime, py, pz will not change, and this px will change as gamma px minus gamma v into E energy. Now so this is the argument of the px prime has changed, and py and pz remaining same, because there is no transformation doesn't change along x, velocity along x direction does not change y and z component. And then the delta x prime you can write in this particular fashion, because this you have gamma px, but energy also contains a px, because energy is √px square plus py square plus pz square plus m square, where you have a px. Now the general rule, probably you have seen in your in many books, especially in classical electrodynamics injection, it is done discussed also, that and used many times, that Dirac delta function of a function of x is given by x minus x naught by divided by its derivative, where x naught is the root of f of x. If you have many roots, then there will be sum over this Dirac delta functions. So here this is as if this is a function of function of px. So you can use this trick, and you can show that it is not the Dirac delta function which is invariant, but the Dirac delta function multiplied by the energy. See, E prime d cube E prime into delta p prime is equal to E delta p. So energy times 3 delta is a invariant quantity. So if you actually, this normalization ensures that if I put here a 2 EP, that ensures that normalizations for that invariance. Okay, so that is what we what is the reason for putting that particular 2 EP, because then if you take p prime, this scalar product of p prime, then there will be EP coming, and this E into this Dirac delta function is invariant. If you don't take this 2e, then you will not get this e here, and then your scalar product will not be Lorentz invariant. So that is why this 2ep factor is put there, so that this quantity is Lorentz invariant, because then I will have a product of Dirac delta function and with the Dirac delta function multiplied by the energy, which is Lorentz invariant. Now, so we are calculating the propagator. So now let us calculate this phi x phi y, right? This particle going from y to x. This all these normalizations which I have just discussed, you put all this, you will get, in terms of annihilation and creation operators. And as I said, only non-zero term will be this a dagger, all these will be 0. Okay, so only this term will survive. And if only this term survives, then you can do this integration, right? These integration measures are coming from the expansion of the phi, and then this is coming from, because this is, a dagger operating on 0 will give you p prime, and the ap operate on this Bragg vector 0 will give you p. So that will give you this 2e times Dirac delta function, and then you can use this Dirac delta function to the p prime integrations, and then what you get is this t cube p by 2 pi cube 1 by 2 ep e to the minus ip dot x. So the probability amplitude for the particle going from y to x is given by this, and this function is sometimes denoted as dx minus y, and this is called the propagator. Now let us see what that propagator means. Now again, let me just calculate this propagator for a space-like domain. You see, whenever I will take the x minus y square, x minus y is a 4 vector, so its square is the length of the 4 vector, and when the length of the 4 vector is negative, that is called a space-like domain. Okay, now for a space-like domain, I want to evaluate that. Okay, you see what we have done here. I want to do this integration, and you have a root over p square plus m square, right? And if this root over p square plus m square, this has a branch cut at p equal to plus minus im, because this will give a solution p square equal to I square m square. So p will be plus minus im. So you have a branch cut here. So if I put here this, roughly I am doing this, qualitatively I am doing this. If I put here im, then what we get, that is gx minus y, this propagator amplitude for particle going to y to x e to the minus m x minus y, right? Because x0 minus y0 is 0, because I have taken a space-like domain. Space-like domain means this 4 vector square is less than 0. So if I take the temporal component 0, I ensure that it is a space-like domain. I have taken this temporal interval equal to 0. So this is a space-like domain. So classically, a particle cannot go out of the light cone, because then you are if a particle goes out of the light cone, then that needs to propagate with a velocity more than the velocity of light, which is not possible. But quantum mechanically, what can happen? It can propagate from y to x. It can propagate, right, e to the minus m x minus y. But what will happen? But if a particle can go from y to x, a particle can y to x, then the particle can also propagate from x to y with the same amplitude, and that cancellation of the amplitude gives you restores the causality. Okay, and we want to see that whether it is really happening or not. You see, so you see what I can calculate here is that now the commutator phi x phi y. Why I am calculating the commutator phi x phi y? Because this term will give me the propagator for y to x, and this will give me the propagator for x to y. Okay, and I want to see whether when that is a space-like separation, when the separation is space-like, that is when you are outside the light cone, then whether this amplitude will cancel this or not, right? So let us see that. So x minus y, again this is a 4 vector. I am taking the temporal component 0 and the spatial component non-zero, And if the special component is non-zero, then you know that this is a space-like domain, because square of this vector will give me negative quantity. Okay, so now let us calculate dx minus y minus dy minus x, and we have just calculated dx minus y. Dx minus y just we have calculated e to the minus I. It is just simply the Fourier transform of this quantity 1 by 2 EP. This is a Fourier transform, or of course there is a half factor, but this is a Fourier transform of this quantity, which is is dx minus y, looking like. I mean, it's not exactly the Fourier transform, but it's like. Because why it is not Fourier transform exactly? Because you have a 4 vector product here, right? But the integration is over 3 vector. Okay, so this dx minus y, particle amplitude for going y to x minus going x to y. This amplitude is d cube p by 2 pi cube 1 by 2 EP. This is the, and then e to the minus p x minus y. This is the x minus y I have calculated, and then this is just, I'll change x minus y to y minus x. Just change x minus y to y minus x, right? Now I put this x minus y as 0, temporal component 0, and the spatial component as x minus y vector, right? So dx minus y minus dy minus x is d cube p. Now this p0, x0 minus y0, that term is 0 because this temporal component is 0. So what I get here, e to the I p dot x minus y, and here e to the minus I p vector dot x minus y vector, right? Now again, you know that I'll change the p to minus p for the second term, and we have done this exercise repeatedly and seen that this doesn't change sign. So what will happen? This will change the sign, right? And if that changes the sign, right, then you'll get dx minus y minus dy minus x equal to e to the I p dot x. Let me just p e to the I p dot x minus y minus e to the p dot x minus y. So same, this is 0. So you'll see it is propagating amplitude for a space-like domain, domain which is not not causally connected. That kind of domain, when a particle going from y to x is exactly cancelled by the particle going from x to y. So in the space-like domain, my amplitude is 0. In the first day we have seen that amplitude was non-zero for any arbitrary value of x and y. But here what we see today is that for a space-like domain, that means the domain which is not causally connected, for that particular case, the propagating amplitude for the particle going from y to x is exactly cancelled by the amplitude going from x to y. So my quantizations of the field, Klein-Gordon, let me now repeat, Klein-Gordon equations I have treated this as a classical field equation, and that classical field equation, when I quantized, right, I got the quantum theory of the fields, and there I see that causality is restored, which was a problem in non-relativistic quantum mechanics. There what was there is that the particle or propagation amplitude was non-zero for arbitrary value of x and y, and that was violating the causality. So when I was trying to combine the quantum mechanics with the special theory of relativity, I had a big problem, but that problem is solved here, because for a domain which is causally not causally connected, there not causally connected, there the propagation amplitude for the particle going from x to y is exactly cancelled by the amplitude going from y to x. So this is fine, right? Now this is a new topic which will be required for our Feynman diagrams, which is called Feynman propagators. This is a new topic. I'd rather going to this, probably I should today what I should do, I should tell you about the quantum-invariant covariant vector, so that that mathematical definitions. But this will be bit mathematical, but you have to bear with me, because that so suppose you have a function f which depends on variable x1, x2. So what I have discussed today, that I have told you that by quantizing, the causality is restored. The propagation amplitude, which is for a particle going from x to y, is exactly cancelled by the amplitude going from y to x in a space-like domain. That is the domain which is not causally connected. Now, tomorrow what I will do, I will calculate this Feynman diagram. This is a very important topic, Feynman propagators, which appear in the Feynman diagrams when you do the real calculations, like calculate the cross sections, calculate the decay rate of particles and all that. It will be required. So that is extremely important. We'll take up that tomorrow. I'll very briefly tell you what is contravariant and covariant here. So consider a function f, which is which depends on x1, x2, and xn. Then any incremental change in delta in f caused by the change in x1, x2, xn is written as a total differential delta f, and in terms of delta f, delta x1, dx1, del f, del x2, dx2, and so on. Okay. And this quantity I can write as this total differential as f1 into delta 1 plus f2 delta O, this sum. For f1 is nothing but this delta f1 derivative of f with respect to x1, and f2 is derivative of f with respect to x2, and so on. And delta 1, delta 2, etc. as are dx1, dx2, dxn. Now let me just write here, tell you that this dx1, dx2, so this f is the gradient, simply the gradient, derivative del f, del x1. These are all covariant vectors, and this delta, they are contravariant vectors. And why they are contravariant and they are covariant? If you want to know that, you have to do some algebra. Like so suppose f is here, this f will be a f which is a gradient, it is a covariant vector, but the dx1, dx2, this will consist of a contravariant vector. Now, if you want to say that, you have to do some little bit of algebra, and that algebra is you make a change of variables, make a change of coordinate system from x1, y1 to y1, x1, x2, xn to y1, y2, yn. Now you know that if you make this change of variables, then this y1 will be a function of x. I can invert this relation and write this y1 as a function of x1, x2 up to xn. y2 is also be a function of this x1, x2, xn. Like when you go from Cartesian to polar coordinate, spherical polar coordinate, this x variable x depends on r, theta, and phi. So similarly here, this x, y will be a function of all the coordinates x1, x2, xn. Similarly, y2 will also depend on all these variables. So if you now want to calculate this y1 is a function of all these x1, x2, xn, then what you can do, you can calculate the differential dy1. It will again remain as del y1 del x1 dx1, del y2 del y1 del x2 del x2, all y1, del y1 del x2 del xn. I would suggest you go through it, and if you have a problem, then let me know. And then this delta for any this one for any I, this will be the differential form, which is very important to it's not very big deal. You can check. Now you see this delta I, which is nothing but this quantity dyi is dyi dx1 and to del 1, right? Where this del 1 I have already defined. This del 1 is dx1. Actually, this works out very well in board, but somehow we don't have the chance to do that. So this is how the y1, this differential in the total differential of this y1 in the new coordinate system will look like. So this is what is happening here, is that what is appearing here, the derivative of the new coordinate system with respect to old one. If such thing happens, then those are contravariant vectors. Like velocity is a contravariant vector. You can understand that in the following way. Suppose you are measuring the velocity in terms of, let us say, kilometer per second. Now you change your scale to meter. What will happen if you change your scale to meter? What is happening actually? Your velocity will increase, but you are measuring it in the smaller scale. Your scale has become small from kilometer to meter, but if the magnitude of the velocity has got multiplied by a factor of 1,000. So that those kind of variables are contravariant. It's not co-varying with the change of scale, and that is what is happening here. Is that for the contravariant vectors, what is happening? The derivative of the new is coming with respect to the old one, right? So this is contravariant. Now for the covariant vectors, again, what you can do, this y1 is a function of all these quantities, right? Now what I can do, I can invert this relation and write down x1 as a function of y1, y2 up to yn. What I did earlier, I wrote y1 as a function of all the other x variables, x1 up to xn, and what I did here is that y1, x1 I am writing in terms of the y1. Again, what you can do, similar thing, just you can write the delta x1 as a delta x1 del y1 dy1 and so on. I mean, it is, you can just check delta xy, you can write in this particular fashion, right? Then the df was what? df was the original total differential. This you please go through it because it's just a few steps in algebra. Del f, you can see, if you can write this as del f del x1 dx1 and so on, right? Now this dx1 is this kind of is long expression. Just put dx1 here. Similarly, df dx2 dx2 also will have similar expression for I equal to 2. You put there, and then what you get this df in terms of the new coordinates at f1 dx1 dy1 and so on. So this, now the gradient, this gradient component of this gradient is becoming f1 del f1 is this df dx1. df dx1 is nothing but the the derivative of f with respect to its old coordinate, and then you see g will be written in terms of this. So this and this will be the gradient in the new coordinate. Now you see here what is coming in the contravariant, what is appearing is the derivative of the new with respect to old, and you see in the gradient, this del f del x1 was the gradient. In the gradient, what is coming is the derivative of the old with respect to new. So they are covariant. So this is the prototype transformation for covariant and contravariant. If you make a change of basis, so see the gradient which we had calculated in x coordinate, x1, x2, xn. Now then we made a change of variable from x1 to y1, and simply what we did, we now calculated the gradient by gradient I mean this del f del x1, and by the dx, and which I called a covariant vector, and dx1 or dxi I call it a contravariant variable. And those two quantities now just I have calculated in terms in the new basis. I see in the contravariant vector what is appearing, the derivative of the new with respect to old, but for the covariant, derivative of the old with respect to new. This is the characteristics of prototype of covariant and contravariant vectors. You see, when you take the gradient co-vary with the co-vary with the coordinates. That's why it is called covariant, and contravariant is just the opposite. Like as I said, given you the example for the velocity. Velocity, if you may have a velocity in kilometer per second, then I ask you, just scale down your system, so that from kilometer you go to meter. When you go to the meter, you have now your scale has become small, but the magnitude has got larger. So this is contravariant. It is varying, not co-varying with the with the scale change. It is contravariant, and the gradient will be just the opposite. It will, if you change the scale, if you scale down the scale, it will become smaller. So that is the whole difference. This I'll send you. It's not no great deal, but it is this algebra you have to do by yourself, so that you know. So what I feel here, I'll stop here today, and tomorrow I'll introduce the most important topic of the Feynman propagators, which is extremely important. And when we calculate the cross sections and decay rates and all that by using quantum field theory, we are just discussing the formalism now. When we will discuss do some real calculations, then and learn to draw the Feynman diagrams. Feynman diagrams will have many ingredients like external lines, propagator, vertex, and all that. And this propagator is one of the ingredients of the Feynman diagram. So this is a very important topic which I will discuss tomorrow. So let me stop here today, and let me know if you have any question.
Dr. Mukleswar, someone has Rajak has asked a question in the chat box. Please convey to this. Mukleswar is there? No.
This causality part is very important. You must have noted that how the propagating amplitude from x to y and y to x is mathematically cancelled once you quantize. That's very important. So if that is the one of the milestone of introducing quantum field theory, that and that solved the problem of the which we had in combining the special theoretical relativity and the quantum mechanics. But this covariant contravariant part, the transformation part, you please the students let them practice by themselves. I'll send the note. Okay, please, if you have any question, let me know.
Dr. Mukleswar, Rajak Loskara asked a question. Please convey to this. He is in the chat box.
So there is a question here about the harmonic oscillator. I can see that this is from the is coming from the uncertainty principle. It is true, what you said is correct, but we'll see that, and probably I don't know whether you were there in the lecture yesterday or probably yesterday I have discussed. I can write down the the Hamiltonian in in such a way that 0.1 energy will not appear. That is called normal ordering. This, as I said yesterday also, I'll discuss when I will discuss the Week's theorem. I'm slowly going towards the diagrams. I'll discuss before that. I'll discuss, but by normal ordering, you can get rid of this ground state energy. This problem which we are facing with the disturbing factor of infinite energy.
Sir, I just have a question that do you have a plan to quantize the electromagnetic field?
It all depends how long we can continue. See, the classical scalar field quantization is the simplest thing. So I have started with that. Just parallel procedure. We can. I mean, in our institute, I had to teach that, but it depends how long you can continue with me.
No,
but unless you do electromagnetic, actually, really, that is the most important theory which we all practice in our almost everyday life. So it should be done. But then let me see. I mean, I have no problem in doing that, but you have to be. Let me tell you a few things. Like sometimes what may happen that I may have some other work or tracing assignment, then maybe I'll skip 1 or 2 lectures, and then maybe if you are ready and join again, we can continue this discussion. There is no problem. I can do it. That is from my side.
Okay. Thank you.
But if if you are interested, if you are with me, I can do that. No problem. I can do QCD, QED, no problem.
Okay.
And QED should be done, I think, because that is what you need.
That is why I just ask you that if
sure, it is
QED
extremely important. Certainly, I'll draw, like, you know, some electromagnetic process has to be done. But I am not very sure whether, because, you know, many things I can skip and jump, but that's what I don't want also.
No problem for us, I think.
Sorry? Sorry?
No.
Mehdi, you told something. I
just tell you that we have no problem about that, because we are very much interested about this lecture. And as you know,
problem, because you know, I am teaching this course in our institute and also the advanced field theory course, so I can continue, but it may take longer time. And I can jump and do a few things, but you know, that doesn't look good. I mean, unless you have a foundation why you are doing this, how the problems are, let us say causality is solved and all that, you will not have a feeling. So but to answer Jayanta's question, I'll do that. I want to do that, but you have to continue. You have to be with me.
No, we are always with you. I mean, it would be very nice to have you with these courses, electromagnetic field quantizations, because with this kind of beautiful algebra, the thing comes that the electromagnetic is quantized, and we have the idea of photon.
Absolutely.
This kind of it would be a very, very nice treat for us.
That is very interesting. That is extremely interesting. How the photon comes into the picture will be very interesting. I'll do that. Don't worry, I'll do that.
Okay, thank you.
Yeah, I think Moidul have some questions. You're raising hands.
Maybe accidental.
Oh, okay.
Okay, so
there is a question. There is a question. Yes, sir. I have a question.
Please.
Is there any difference between p-form and p-rank covariant vector, or it is simply two names for the same thing?
No, if it is a orthogonal system, there is no difference. But if it is not orthogonal, there is a difference. Okay.
Thank you, sir. Okay.
That in the last 2 pages of my lecture note today, I have done that algebra in detail. And if you do that, you will know why it is called covariant and contravariant. Covariant, why it co-vary with something, then it is called covariant. Contra is, you know, just the opposite. So it's done in detail, but those line by line, I have done it line by line, but you have to see. Yeah.
Okay, sir. Thank you, sir.
I think there is a question in chat box from Miss Ifat Nasrin.
Sir, in Lorentz transformation, we are representing the 4x4 matrix in terms of hyperbolic functions, sir. Could you please explain how hyperbolic function is related to the... No, hyperbolic function as such is not related to the causality effect. What I am saying here is that if you read the, you know, group theory, you will see Poincare group especially. There you need to, like, you know, the rotation, you know. Now, with certain angle theta and all that, you know all this. Now, what one does there, one can show that the Lorentz transformation, Lorentz boost, we are just boosting something, right, with a velocity v. That can be seen as a rotation with imaginary angle, which is just a, you know, it has nothing to do with the causality in directly. But the Lorentz boost, like we write this, you know, this say x prime is gamma x minus gamma vt, and t prime is gamma t minus gamma vx. What one does actually, gamma one defines as the cos hyperbolic y, and when this hyperbolic function is coming, that means the angle is imaginary. And then if you write down this cos gamma and gamma v in terms of cos and sine hyperbolic function, you will see that this has very similarity with the rotation in 2 dimension. Only difference is that as if the rotation is by some imaginary angle. and that imaginary angle is called the rapidity, you know, because tan hyperbolic y, if you check my note today, tan hyperbolic y is just the velocity. So then since tan hyperbolic y is velocity, that means y tells you how rapidly, how fast the particle moves, because tan hyperbolic y is tan hyperbolic inverse v. So and the one of the advantage of introducing this rapidity, you know, is that when you add the two velocities relativistically, like v1 and v2, you write down this as v1 plus v2 divided by 1 plus v1 v2 by c square. Right? It's not a addition, simple sum like it happens in Galilean transformation. Now, if you define two rapidity corresponding to velocity v1, the rapidity, let us say, is corresponding to velocity v1, I define a rapidity y1. That means my tan hyperbolic y1 is v1, and corresponding to velocity v2, I define another velocity, rapidity tan hyperbolic v2 is equal to y2. Then the velocity addition v1 plus v2 by 1 plus v1 v2 by c square, if I transform that to rapidity, it will be just net total the sum of the, it will be just the sum of the rapidity y1 plus y2. So what I am trying to say is that, like this complicated velocity addition in relativistic theory, if you go to the rapidity by just through the transformation y equal to tan hyperbolic v, then instead of adding that velocity in that complicated sense, you just can add the rapidity as y1 plus y2. So in terms of variable y1 and y2, it looks like you are again in the Galilean transformation. It becomes very simple. That is the reason people introduce this y rapidity, which is actually as if the rotation with that imaginary angle y is the Lorentz transformation. So Lorentz transformation is rotation by this imaginary angle y, which is called rapidity, and this rapidity for two frames is just sum up as happens in Galilean velocity v1 plus v2, it will just become y1 plus y2. That is the reason it does.
Another question from inbox is from.
Can we introduce the concept of expanding universe in QFT? This is an interesting question. Now, you know, what we are doing quantum field theory in vacuum. Now, the expanding universe, if you consider the universe, especially the early universe, especially the early universe, then it is very hot at finite temperature. Then there is a field theory for that, which is called the thermal field theory. That is extremely interesting, but that is beyond the scope of this lecture. Maybe after 1 year or so, if you are interested, again, I work on that field, so I can again deliver some lecture on thermal field theory. Now, so that is for early universe, that cosmology, the thermal field theory you have to learn, which adds some more complexities to this field theory, and that's it. I mean, you have to use the thermal field theory there, and many people are doing that. Thermal field theory is different from which you are discussing there.
And also, sir, is it correct that if we want to introduce QFT in the case of expanding universe, then you have to consider the case of curved space-time rather than flat space-time?
You have to certainly that is there, of course. Your framework should be the Einstein's equations, the general theory of relativity. Certainly. So you have to do the thermal field theory in curved space-time. You have rightly said, yes. But even suppose in the laboratory also, if suppose you are dealing with a very hot system in the laboratory or very dense system, right? Like let us say not in the laboratory, but let us say in the core of the neutron star or any compact astrophysical object. There, if you want to do the field theory, then you have to introduce the thermal field theory. That will give you better result. Yeah. Like you see, when you put an electron in vacuum, its mass is 0.5 MeV by c square. Now, if you put the electron in the solid, because of interaction, its mass gets changed, right? Now,
Right.
how the mass of a particle gets changed when you put in a thermal bath, that will come from thermal field theory, first principle. Probably
Okay.
tomorrow I'll indicate that when I'll discuss the Feynman propagator.
Okay. Thank you.
Hello.
Do you work on ADS safety, or can
Sir.
you please suggest some? Now, I don't work in ADS safety. Certainly, there are many books. I can tell you. Yeah. So tomorrow I'll there is a very nice lecture note. Archive number I'll give you tomorrow for this ADS safety.
Any question from audience or the participant? We shall thank. Meet tomorrow at 30 p.m. Is
Yeah.
okay?
Okay.
Thank you, Professor. Thank you, everybody.
Thank you.
Thank
Thank
you.
you, Dr.
Thank you.
Professor Raman, for chairing the session. And I thank again to Professor Alam for his continuing very nice and lively presentation. And we are learning very beautiful thing, actually new thing to us, because I have not gone through this field theory. This is the first time I am attending, and it is quite interesting. Thank you.
Thank you.
Okay. Thank you all. Good night.
Good night.
Yeah.